This is the 42nd video in a class on single agent search. And in this video, we're going to be looking at an algorithm called reach. And this was originally described as something called reach for a star. So nice little pun there. And this is a paper from 2005 coming out of the road networks community by Goldberg, Kaplan, and Wernick. And this is, again, looking at an idea that can be used as a constraint. So this falls in the class of constraints, which is why we're talking about it here, showing how we can use constraints to reduce the size of the space that I need to search. And in order to look at this, we're going to have to think about what the notion of reach of a node is. And so the notion of reach is a little bit complex. I'm going to give you a high-level motivation for what it is, and then we'll look at a low-level description of how you actually compute this. So let's imagine that we have a country. Let's say we have a country that's shaped something like this, whatever country this happens to be. And what we're thinking about is traveling all the way across that country. So maybe there are a couple different ways that you could travel across this country. But if we think about this, when we are taking a path, we're taking maybe some really long path across the country, then we're going to be ending up on, we're going to be doing this on a freeway, because freeways are basically the fastest way to get from place to place. And freeways are sort of like these long, there's these long channels that will could take us all the way across that country in an efficient way. And if we think about it, if I'm sitting halfway across the country in the middle of in the middle of a desert or something like this. So there's a number of different deserts or other places where there aren't large populated areas. And I think about what would happen if I were to get off the freeway at some point here? Well, if I think about the shortest path, practically speaking, is that this getting off of the freeway here is likely to lead me to some set of states here that are locally going to be within my search. But this getting off the freeway here is very, very unlikely to be efficient for some sort of very long distance travel that is going all the way across the country. Okay. So if I know my goal is really far away, if I'm going to get off the freeway right here, it's very unlikely that I'm now going to take these little small roads here and actually get somewhere productive. But if I actually run something like a heuristic search algorithm, and try to run it on a map like this, if we think about f-costs, the f-cost here may not be quite perfect because maybe I'm not ending up exactly on the freeway. I'm ending up somewhere that's a little bit ways from a freeway. And so if I'm a little bit a ways from a freeway here, practically speaking, what my search is going to think, given no extra information, is that, well, maybe along this freeway here, if I were just to travel a little bit distance over here, I would find another freeway that would take me directly to exactly where I wanted to go that would be much more efficient. Maybe if I hop off the freeway right here, there I go, I get directly to my goal. I do it very, very quickly, and it's going to be much more efficient than this actual big freeway here. Practically speaking, though, we know that freeways are very expensive to build, so it's unlikely that's going to happen. And we also know where the freeways are ahead of time. The freeways don't change very often in a larger scheme of things. And so I'm not going to expect that I'm going to actually find another freeway there in practice. And the thing is how could I encode that? How could I encode that practically speaking? Well, if I get off the freeway here, I always can just get back on again. And so, there is some path here that is just fractionally larger cost than the cost to, the cost to get to maybe my goal. And when I think about getting to some place out here, my search might be willing to consider this because it's just, fractionally more expensive. And so it's less expensive to add this get on and get off the freeway here than it is to actually get from the end of the freeway to maybe my final destination at the end. And so what's going to happen is the search is going to look at all of these possible things that are around the freeway going across this country. And so they're going to do a lot of work around here, because they're thinking about, well, maybe if I go over, any inefficiencies that are generated by the freeway, if I just sort of go over here, maybe I'll find a better freeway In practice, we know that's not going to happen. So we'd like to do some computation. And the idea here is if I get off the freeway right here, it's not going to get me very far. Like that's only going to be useful if my goal is right in this region right here. It's not going to be useful for going anywhere else. And so what we're going to have is the idea of reach, where reach basically says, look, these states inside here, they have low reach. They're not going to reach very far. And therefore, I should only consider them if I'm very close to my start state or very close to my goal state. Okay, so reach is a measure of basically, it's an estimate of distance to the goal. And so this is very similar to what the last video was looking at for bounding boxes. When we think about bounding boxes, we can just say, it was said, I should only take this action if the goal is in some particular location. Here, again, we're going to be using something similar. So let's think about a path P. So for a path P, okay, which is going to go from S to T, from vertices start T. Well, we'll just use ST, and T doesn't mean the goal necessarily, but, this is coming from a community that likes to use ST, more thinking about a graph than where we would use start goal from more the AI or heuristic search perspective coming there. Okay, but we're thinking about a path from S to T, and then we think about a vertex. So we've got this path that's going from S to T, and then we have some vertex here that we're thinking about. And we want to say, what is the reach of V with respect to this path P? And so the reach that we're thinking about is a picture of what can happen here. And so for one particular path, what we're saying, well, look, this is the distance. I have the distance to go from V to T. And I also have the distance from S to V. We can do this in both a directed and undirected way. And so this is written in a sense a directed way from S to V and from V to T. We could also think about these distance, as I said, in an undirected manner. But so we're thinking about V. We're thinking about how far did it take to get from the start? How far is it going to take from V to get me to my goal or to T? And what I want to keep track of is sort of what's the minimum of these values. So for V and a particular path P, we want the minimum of the distance from S to V and the distance from V to T. And then, so this is the reach. So this is reach of V with respect to P, a single path P. And then what we're going to think about is, well, what is the reach of a vertex, not just V with respect to P, but the reach of V overall. Okay, so the reach of V overall is basically going to just say, look, for all P in my all possible paths in the world, then I want the minimum of the distance from S to V. So just to be clear here, let me write this slightly differently. So this is going to be P is some path. So we want really P, the S on that path, to my vertice, and the distance from my vertice to the T node at the end of that path. Okay. So I wrote my distance twice here. To the path's T node. Okay. So what we're going to do, and we're going to take the max over all of these, and what this is going to say of the minimum. So the reach of V is the maximum over all possible paths of the minimum distance either to the start or the goal. Okay. And so what this says, it says we think about like all possible shortest paths. So I have to be really clear here. P is the set of all shortest paths. Okay. Sorry, I'm writing crooked today. So P is all shortest paths. So we think about all shortest paths. Now, where are all shortest paths? We think about all shortest paths going all the way across. There is going to be no shortest path that goes halfway across this country, gets off, gets back on again, and then goes quite a long distance here. There's going to be a shorter path by just going straight across. So if a path is going to get off somewhere here, it's going to end up that the goal should be, or the start should be somewhere in this region right here. And because we're going to take the minimum of these, if all the goals are somewhere close by here, or the starts are somewhere close by here, then this state is going to have a low reach with respect to any individual path and also with respect to any long path. So if I'm taking some really long path, the question is, would I ever take this state as part of a really, really long path? And the answer is no, because there's other states that will take care of our really long paths. So reach is telling us basically, hey, when I'm going to take a really long path around the world, how far must I go? Or what's the minimum distance that I could find for any state that would be sort of the farthest state that I could get to on this path, from a particular state, what's the farthest state I could get to on an optimal path, given that the other state, whether it's the start or the goal, is at least that far distance away. Okay. And so what I get as a constraint here, there's two different things. So as a constraint, what we're going to think about is we have two different possibilities. So I've got a vertex V, I want to expand it. And now we're thinking about our search. So we have the G cost of V is going to tell me the cost to get to V. And so if the G cost of V, which means the path so far, is less than or equal to the reach, so this is R of V over here, is less than or equal to R of V, that means this state, the start state, so I'm close to the start state, and the reach is greater than the distance to the start state, then we must expand the state, or it's eligible. The other thing we can say is now here, I don't actually know the distance to the goal, so I'm going to use my heuristic for this, although we could build a better heuristic to improve this. If h of v to the goal, okay, the heuristic is less than r of v, then this also says we must expand. Okay, so here's my two conditions. I guess I don't need the if on the second one. So move this over. We have two conditions here. One is that we're writing it this way, two conditions. One is I have to generate, if the G cost so far is less than the reach, then this is a state that we're thinking, let me just say, the reach is like a radius around a state. So if the reach here is small, then basically I'm drawing a circle here. And I'm saying, look, if the start or the goal is inside this circle, I have to expand this state. So if I have a state here and the reach, which is like a circle around here, because we're using actual distances here, it's not truly a circle when it comes to the start state. But if the start is within that circle, then I say, that circle, that state could be on an optimal path through here. There could be an optimal path going from the start to here to some other state, and therefore I have to expand it. And what this is saying is, here it's saying, look, I don't know how far it is to the goal, but I think it's at least this far. And this is a lower bound. So then we say if the heuristic is less than the reach, then I still must expand the goal as well. Now, with regard to the heuristic, it's possible, right? So the heuristic could be a lower bound, and it could actually be that the state's distance to the goal is actually larger than the reach. And so, so it could be that maybe I'm not supposed to expand the goal. But because the heuristic is a lower bound, when the heuristic says is less than here, if I always expand that, then I'm guaranteed that I won't make any mistakes. If the heuristic is greater than the reach, I'm guaranteed, because it's a lower bound, that this state will never be on an optimal path between the start and the actual goal state here. Okay. And so, so we can think about reach as being a radius, and it says, look, for any given state, the radius has to be, the start or the goal has to be within the radius of that state in order to say that it has to be expanded. And so states that are on the highway here are states that really can reach quite a large distance in my map. They'll have very large reach, and they're going to say, you can get all the way across your country if my reach is very large, but it could be there's states right next to it that have very small reach, and therefore I will never generate these states that are right next to it. Okay. And the best way to understand this is actually to look at some pictures. So we're going to look at two pictures here. And interestingly here, when we generate this, we can actually generate reach, perhaps unsurprisingly given the previous example, but we can generate reach both using canonical ordering and not using a canonical ordering. And so here, if we look at this picture, this is a map, and the darker the color, the higher the reach. And so what we can see here is anything on the border of the map, if you're going to, if you're going to go down into the corner, if an optimal path goes through that state, then the start state or the goal state is going to be very, very close by. And I don't need to expand those states. But if the state is right in the middle of the map in these dark red regions, then those states are part of very long paths that go basically from the top to the bottom of the map. And a little bit less we see, so from the upper left to the bottom right, a little bit less we also see from the sort of upper right to the lower left. We see some paths there. Now, if I take into account the fact that I have canonical paths, and I'm only going to follow canonical paths, then we can do a little bit better. And what you see that does is it eliminates this space in the middle, because we know that, like when I'm going from the upper left to the bottom right, if I'm going upper left to the bottom right, I'm actually going to take, I take my diagonals and then cardinals. And when I go from the bottom right to the upper left, again, I take diagonals and cardinals, but there's a space in between that I won't actually take in either direction. And so we're able to reduce the reach of some of the states inside there, because I'll never actually use them on my shortest paths. And so what we can see here is that the actual reach of many states is quite small. And so let's just look at this. I'm going to run a video here. So we'll see the original and then the canonical reach. If we watch A star solving one particular problem here, then what we're going to see is A star is doing a massive amount of work. In particular, what we see is A star is going down into these areas, these rooms that are in the bottom left of the map, that actually we know are dead ends. They aren't really leading anywhere. And so if we add reach to it, we know that those rooms have very low reach, and those rooms are a long ways from both the start and the goal. So as I solve this problem again using reach, what I see is that the open list is entirely pruned coming down and into these rooms on the bottom left-hand side of the map. And so they're entirely pruned from the state space until we get to the very last room here. So I paused it. We can continue here. We see we go down into this last room. And the reason why is because the actual distance, the heuristic to the goal is fairly small there. And so it looks like I can actually maybe get to the goal because the heuristic is misleading. If the heuristic was more accurate, we wouldn't go down there. But we do because the heuristic is not accurate until we come around here. So this is the work that we do using reach, and you can see we get a significant savings over not using reach. And then if we use the canonical ordering, or the reach that comes from the canonical ordering, so the amount of data that's stored is the same, what we'll see here is that we even do better because we don't actually fill in these regions. We go on the outside. We sort of naturally follow the canonical ordering as we do this search. Okay, so reach is another constraint that we can use. And it's, as a constraint, it allows us to prune successors in the map. It allows us to reduce the branching factor of the state space, and allows us to prune out large areas of the state space that we might normally reach. Reach is based basically on a radius, and it says either the start or the goal will be within this radius from a particular vertex. Now notice here that reach on this map is a number which is a single number per vertex. But we could also do reach as we did with bounding boxes, take a vertex and an edge and ask the question. In fact, you could even, vertex and edge, and in a parent even, you could say, given a vertex and an edge, we could also compute reach in that way. That would increase the amount of storage we need, but it would give us even better pruning. So the storage used for reach here is much less than is used, or given a particular branching factor, it's less than we're using for bounding boxes, because here we're storing only a single number. We're doing the undirected calculation here. But as I said, if we didn't use that, we could do better. But the idea here, as I said, reach is just another constraint. And so we see that constraints are actually very powerful. There's many different ways that we can commute them, and there's many different types of constraints that we can get. And in future lectures, well, we're sort of getting towards the end of this class, but in some of the future lectures, we'll be looking at other types of constraints and other ways that we can use constraints that arise, and that we can use them to reduce the size of our search. And so I haven't even, as I said, there's many different other constraint methods that have been proposed and that are very effective in understanding where places in the state space that are redundant to go to. And so we'll continue to look more at this in upcoming lectures.